Okay, so I forgot to change the title of my slide bit. I'm just going to be talking some recent results and going over what I think are some of the major gaps in the geology, physics, and modeling, especially as these new results show. Next chart, please. So in the early research, going back to the Apollo days, we noted that there are several different regimes in PSI. Uh, I like to use the analogy, if you try to drive your truck on a lake in Michigan, you'll have a completely different result in the winter or in the summer. And that's because water undergoes phase transitions. And so you can drive on the ice, but you'll splash in the water. So granular materials also go through phase transitions, and it's a very complicated material. And so depending on the conditions of the plume and the environment, you can induce or not induce different phase changes and different phenomena and get drastically different results. What I'm going to be talking about in this talk is only surface scour. It would be analogous to sublimation, where granular solid is being sublimated at its surface, producing a granular gas. But there are other phenomena which could be collectively called deep cratering. We did not see these in Apollo, although there was some evidence that a little bit of this occurred during the final moments before engine shut off. We could see blast of soil, including dirt clods blowing away, falling apart as it blew away. So there was some bulk removal of material in the final moments, but generally it was just surface scour, and that's what I'm going to be talking about. Next chart. Okay, so this erosion on the surface of a planet has been greatly studied, not only for Earth, but also Mars and Titan, for Triton. Even Carl Sagan published a paper on this. But the erosion by a wind, for example, here on the Earth, is dominated by saltation, the transport of energy from the gas to the surface is rather small, but the grains that are lifted accelerate and then they fall back to the surface carrying energy with them. And that is the dominant source of energy flux from the gas to the surface. Well, next chart, please. In a lunar landing, the rocket exhaust is so fast that the particles may fly many kilometers before they impact the surface again. And so they fall where the gas is already expanded into vacuum. And so there's no saltation. So it's fundamentally different. And if you review the literature on erosion here on the Earth, you'll find out that saltation is the dominant energy flux, and all the correlations are based on that regime, and it doesn't apply to this situation. Okay, next chart. So the first question then is, what does govern the erosion rate? And I want to make a distinction between the rate that particles get lifted off the surface. We could measure that in kilograms per square meter per second, and then the rate the particles get accelerated to. Both of those processes are using energy and using momentum from the gas. But we need to make a distinction between them, as you'll see later. So the first theory that was published on what governs the erosion rate was by Leonard Roberts from NASA back in the 1950s and 60s. And he argued that those two processes are actually closely coupled. And so he said the erosion rate, dm/dt, which is kilograms per square meter per second, is proportional to the excess shear stress in the gas, because he said that the particles would be sheared along the surface. And so it's a shearing process. And he said there's a threshold, which is the shear strength of the soil. And then there's the parameter A, which is proportionality. And he said that A, it would be the final velocity that the particles achieve in the gas, because as they're accelerated, they use up momentum for the gas, which lowers the shear stress until you reach equilibrium. And that determines the erosion rate. So the acceleration of particles in the gas is what governs dm/dt. There's two problems with that theory. First of all, erosion is not a shearing process. Particles are not sheared across the surface in general. They're lifted from the surface. They don't necessarily rub along the surface at all. Second of all, the ejected particles achieve their final velocity far downstream from where erosion occurs. So there's no way that accelerating the particles downstream can govern the erosion rate upstream. Next chart, please. And I don't want to go through over this in detail. You can look at the two papers that I recently published in Icarus. They're referenced in the abstract for this talk, but there's evidence that erosion is a low energy process, which is surprising because rocket exhaust is a high energy gas flow. Next chart, please. So we started doing experiments way back like 20 something years ago using a splitter plate where the gas would be, circular jet would be split in half, and that allowed us to see inside the crater. No experiment is perfect, and so the deepest part of the crater is actually slightly behind the glass, but it's not that bad, and so it's a pretty good experiment. Next chart. What really makes the experiment nice is that you naturally, in most cases, in a broad part of the parameter space, you get a dual shape or a two, I can't think of the word. You get an inner crater and an outer crater. And so what's nice about this is that the inner crater stays constant size and shape throughout the entire experiment. All crater growth is actually in the outer crater. Next chart. And that's important. Well, you can see that because the left shows the depth of the overall crater versus time at 4 different gravities. As you would guess, Lunar is faster crater growth than Mars, Earth, and 2G or 1.8G. On the right, you see the crater width. The outer crater is the upper curve, and the lower crater is the scattering data. I mean, the inner crater is the lower set of scattered points. And you can see the inner crater reaches a constant size, and it just oscillates around that size, whereas the outer crater continues to grow. The reason this is important is, next chart, the gas only interacts with the inner crater. And so the erosion rate is taking place on a surface which is roughly constant throughout the entire experiment. And this solves a problem with wind tunnels that as you erode, you're changing the shape of the surface in a significant way. So this is just nice. And then also, fortuitously, we discovered some other factors that made this into a nice experiment. By the way, I want to point out here that the erosion rate is fastest at the lip of the crater. You can see that these are plots of the gas velocity, and the gas velocity in yellow is the highest right at the lip. Okay, next chart. Now, the inner crater is steeper than the angle of repose of the sand. And the reason it's able to be steeper is because the traction of the gas stabilizes it. The outer crater is at the angle of repose. Now, all the primary erosion is occurring at the lip of the inner crater, but the inner crater, as it gets deeper and wider, the traction is spread around a larger circumference, and so the lip becomes unstable, and it's not able to remain steeper than the angle of repose. So you get avalanching. And when you get avalanching, that entire surface of the outer crater peels off and avalanches down into the inner crater, gets turned around by the gas flow and blown out. And that's the secondary erosion. So all the primary erosion is on the inner crater, but the net crater growth is due to the secondary erosion. What's interesting is that you can prove, I won't go through it here, but in the paper you can read, you can prove through the data that the rate of erosion in primary erosion is constant throughout the entire experiment, although the rate of loading of the gas from particles from secondary erosion is growing continuously during the experiment. So the rate of erosion is insensitive to the rate of momentum being taken from the gas by the secondary erosion. And this directly disproves Robert's theory. Next chart. Also, so that then leads us back to the question, well, what then is the rate governing part of the physics? So we did these experiments varying one parameter at a time and getting erosion rate scaling equations. The numerator shows us that, and at top line, the numerator is rho v squared times the exit area of the pipe, and that's the momentum flux into the experiment. The denominator is all properties of the soil, density of the sand grains times gravity times an average particle diameter, and we measured all of these directly. The numerator, it turns out, is proportional to the local traction everywhere in the experiment, so you can make that substitution. Now, for dimensionally, it turns out that the constant c has to have units of velocity. And so 20 years ago or 10 or yeah, it was 14 years ago, we were saying, what is that velocity? Is it the, like Leonard Roberts said, is it the speed of the particles? Is it a something about the gas turbulent eddy velocities, or is it the speed of sound in the gas, which is the molecular thermal velocity? Later, we did reduced gravity experiments. The second line of the equation in the denominator, there's a plus alpha. We found out that when gravity is small enough, then it falls off of that curve. And so we hypothesized there must be a plus alpha in the denominator because the left-hand side of the denominator is potential energy per volume of soil. Therefore, the right hand must also be an energy term. And so we hypothesized that's the cohesive energy in the soil. So anyways, I don't want to go through all the details that's in the paper, but you can write the equations for stability of the inner lip of the crater. That's what the next two lines are, and derive a power law for the traction of the gas at that lip as a function of crater width. And then when you do the ratio of that equation at two different gravity levels, substituting the stability equation, you get that bottom line. And so the term in parentheses is the ratio of the numerators, and it's measured in crater widths, which is directly measurable. And the right-hand side is the ratio of the denominators at two different gravities. So we want to find out, what is D? Is it really an average grain diameter, or is it something proportional to average grain diameter? And then what is alpha? So next chart. So hypothesis that alpha is cohesion. There's something I want to talk about cohesion later, about what are the different types of cohesion. But for now, let's just say that we are estimating this as the van der Waals force, although electrostatics probably plays a role. So there could be a factor of 2 or more error because we just assumed van der Waals. However, the electrostatics are going to be vastly different in different environments. So there's not much we can do about this until we get data from the moon and the plasma environment anyways. But so you can write the van der Waals equation. Next chart, please. You can integrate it over all the particle sizes in the lunar soil, assuming some contact to contact model. And it comes out to about only 0.23 joules per cubic meter of soil, which is very small. That potential energy term is also extremely small. And so putting that into the equation, we can, and using the empirical data from the reduced gravity flights, you can solve that D is about 270 microns. So D is the height that the soil has to be lifted for it to be blown away, and alpha is the energy used pulling the grains away from each other. These are both extremely tiny energies, so that numerator must also be extremely tiny, which is the energy flux of the gas. Okay, next chart. And what this tells us is that what happens to the particles higher than 270 microns does not govern the erosion rate. Okay, so the model is that particles are being sheltered between the coarser particles. There is the gas flowing in between the grains is creating stagnation. That pressure pushes the particles up over the coarser grains, and they get blown away. There has to be enough stagnation to create the energy to overcome the potential energy and the cohesion. Next chart. I'm gonna have to fly through this. I'm down to 2 minutes. Okay, so this gives us the completed erosion equation. We know that close to the surface, the only other velocity that exists, because you are definitely in a laminar flow condition that close to the boundary, both in the terrestrial test and in the lunar case, the only velocity it could be is thermal velocity of the molecules. So that tells us that using the laminar equation for energy flux, we get a completed equation where the coefficient epsilon is now a constant, which we can measure directly from lunar cases. So let's go to the next chart. When we apply this to the moon, we can look at pixel brightnesses as a metric of the amount of dust. Next chart. Next chart, please. Okay, so writing the geometry at each moment during descent, the sunlight has to go down through the dust, hit the soil, and come back up through the dust again. At each point that it passes through the dust, that point was fed by dust from numerous erosion locations on the surface, and the light has to go down and up again. The equation at the top is the camera model. The right-hand term is the attenuation of the sunlight going down and back up again. The left-hand term is multi-scattering in the cloud. Next chart. Okay, so there's what the integral looks like. You can see the dominant results are due to dust that's finer than 10 microns, which unfortunately is not well constrained in lunar soil. Next chart. And when you do the curve fitting, there are 2 parameters. And so there's some degeneracy, but it only produces about a 30% error, and you naturally get an extremely good fit. Next chart. The problem is that when you extrapolate that down to touchdown, it predicts a 5 meter deep crater, which we know didn't happen. And that's because you're initially blowing this tiny, weak dust off the surface, and then you're getting down into the more resistant soil. And so there needs to be a term in the equation to slow the erosion rate. Next chart. And I know I'm out of time.
Do you have a wrap-up slide?
Yep, give me a couple of seconds here. So you need a model of the soil. You need a model of the soil. And so using the diviner data, lunar source book data, next chart. We have to infer a relationship for cohesion as a function of compaction of the soil. Next chart. And that introduces another parameter, K. We need to have another data set, and that's looking at the soil to see how much eroded. You can only estimate it very crudely. Next chart. Next chart. And so looking at the variety of plausible cases, final chart is that it tells us, next chart, please. It tells us that somewhere between 25 and 11 tons of soil were blown. But the most uncertainty comes from that cohesion in the soil, which is not well constrained. And so there's about a factor of 3 uncertainty because of that. So I'll just not go to the final charts, and I'll just say that the gaps in the physics, the most important gap is the fluffy state of the soil and the amount of cohesion in the top 6 or 12 centimeters of soil. And we really don't have any good data sets on that, but that is the largest source of uncertainty. The next largest source of uncertainty is that we don't have good constraints on the inventory of particles down to 0.3 microns in size up to about 3 microns in size. And there's also a lot of gaps in the uncertainty in the modeling methods. Okay, I'll just skip the rest. So sorry I went over.